Thank you very much, Sanjib, for the introduction. Thank you very much to both of you, Abhishek and Sanjib, for the organization of this school. So, good afternoon or good evening, good morning to all of you. So during these lectures, indeed, I will try to cover. I was asked somehow to cover these three topics which are in the title: Dyson's Brownian motion, fermions, and randometric theory. In fact, indeed, the common tools behind all these topics that I will touch upon are indeed the randometric theory, and therefore I decided to start with a short crash course, if you want, or introduction to randometric theory, at least on the basic features and tools that we will need in the following. I thought that it was probably not that maybe not all of you are familiar with that, so I will start with that. And I guess that I will probably need, say, 2 lectures to do that. I mean, I will see how it goes, and that will give us, say, a good background, I think, to start with. And then the second subject that I will that I will talk about are around fermions, which is a topic that we have been working quite a lot during these last years with my colleagues and friends. Satya is here, and also other colleagues, Pierre Ledoussal, David Dean, and many other students. But I will try, of course, to stay quite elementary, and I will try to show you that fermions actually are very nice applications, and that they have very natural connections to randometric theory, and that also sheds light somehow on how to understand randometric theory for a more physical point of view, maybe. So that will be, I guess, lecture 3 and 4. We will see how it goes, but that's what I have in mind. And then I will end up with maybe what is technically also the thing which is, I think, a bit more involved, which has to do with a non-intersecting path. And that will naturally lead us to the connections with randometric theory, and in particular with Dyson's Brownian motion. Okay, so that's somehow, if you look a bit at the title, instead of going in that direction, essentially I decided to go the other way around because I think that it was conceptually more natural to do this way. Right. So let's start, and let's start with these first lectures, probably 2 of them, as I said. So that's the outline of these 2 first lectures on the randometric theory, which is usually called RMT. And I will start with a general overview and show you some applications briefly on RMT. I will not enter into the details, but just to set up a little bit to tell you where it comes from, what are the main questions in this topic, and then I will be a bit more precise and discuss some ensembles of RMT. I will basically show you first some Wigner ensembles, and then I will discuss the rotationally invariant ensembles, going to the Gaussian orthogonal and unitary ensembles in particular. And that will bring me to this coulomb gas approach, which was devised by Dyson in the 60s, and to show you really how this problem of randometric theory, which initially, at least to some extent, is a purely mathematical problem, can be understood in a very physical terms. In a relatively simple way, using this mapping to a Coulomb gas, and then use the standard tools of statistical physics. And then I will, and so I think that I hope I will have time to cover these three steps today, and then I will spend quite some time on what I call local statistics, where I will try to discuss these 2 very important notions, which are the bulk and the edge, And in particular, looking at the edge, that means that looking at what happens at the border, at the edge of the support of the density of the eigenvalues. That means if you look at the largest eigenvalues, I would like to discuss the tracy rhythm fluctuations and its various applications, which became very popular during now the last 15 to 20 years. So that's the program, and let's start with a brief introduction. So basically, the topic of random matrices is quite simple to explain. I will just consider capital M, which is say n cross n matrix, and it's random in the sense that the entries are random. Okay, and I will generically denote them MGK. And note that these guys, in principle, that can be real or complex. And then there are various questions that you may you may ask about these random matrices. Typically, you would like to say something, and that's what random matrix really is about the statistics of eigenvalues and eigenvectors. So that's really the main goal of random matrix theory. And in particular, in many cases, in fact, in most of the cases, we will be interested in the limit when n goes to infinity, because we will see that, I mean, from a concrete applications, I mean, usually when the interesting applications really imply large matrices, as we will see. And that's also in that limit that nice collective and nice effects will emerge. So that's really what we are after. Now, this problem, as you probably already know, has many applications, but in fact, in physics, it was introduced by Wigner in the 50s. And as you probably know, what he was interested in is in the context of nuclear physics, where you are interested in understanding the spectra, and that means trying to solve the Schrödinger equation, if you want, for big nuclei. And he introduced this approach to essentially model the energy levels of big nuclei. And the idea was that you have, if you want really to solve the Schrödinger equation for such a nuclei, I mean, of course, you can imagine that it will be very involved. I mean, you will have complex interactions between the nuclei, the nucleons, and therefore he proposed to say, okay, let's forget about this kind of microscopic detailed approach, and let's try to see what happens if we say that, okay, the system is so complex that it's probably a good approximation to treat it as a random system. And if it's random, then the spectrum of the Hamiltonian will be itself random. And then it turns out that this approach was extremely successful. And after that, this kind of approach, that means studying random matrices to various physical systems, became extremely popular. And since then, there has been a lot of applications. Okay, so that's what is really, oops, sorry. So that's really what I want to, whoop. So there are many books, and there is, for instance, the Oxford Handbook of Random Matrices. I can leave you some references later on. One set of examples I just want to give some of them where random matrices arises naturally. One is in the context of mesoscopic physics. So basically, what I have in mind is that you can have, say, a quantum cavity, which might be more or less regular, and you have to imagine that you have some electromagnetic waves that are sort of arriving there. So let me just denote it. So suppose that you have some kind of plane waves, Ki, and then essentially when they enter this quantum cavity, they will experience quantum scattering. And then at the other side here, you will have some outcoming waves, K prime I. And a quite natural way of characterizing this quantum scattering phenomenon is just to say that there is a matrix relation between this vector K prime in terms of the incidental wave vector K, and basically they are connected by a scattering matrix. And if this quantum cavity here is sufficiently irregular, which is quite often the case, then basically that will be a good approximation to say that this S here is a random matrix. Okay, so that's a quite natural example that you might think of. Another example that I will just touch upon is the case of random graph. Okay, so typically a graph would be characterized by some adjacency matrix which characterizes basically the topology of the of your network or your graph. And again, if this graph is random, then this adjacency matrix will also be random. Okay, so these are rather natural examples where you see that random matrices occur. There are also other typical examples of, for instance, a localization problem in quantum mechanics, where basically the notion of a random matrix appears quite naturally. Now, rather remarkably, it turns out that random matrix ideas have also emerged in a variety of contexts where there is no obvious random matrix behind the problem. So I will just mention a few that I will, of course, not have time to treat in details. But for instance, random matrix theory has popped up in number theory. And there are, in fact, very nice connection between random matrix theory and the Riemann zeta function. Oops, sorry. So that's a place where you don't see immediately some RMT or random matrix model, but it turns out that there are, and there are very deep connections. Another example where it's not completely obvious that random matrix theory can play a role is in the realm of combinatorics. For instance, if you look at some interesting observables in the context of random permutations, such that the longest increasing subsequence in such permutations, then people have shown during the last 10, 15 years that random matrix theory was also there. And in fact, so these are relatively mathematical problems, but one instance of RMT, which in the context of physics, which is, I think, particularly interesting, and I hope I will have time to say a word about this, is in the context of fluctuating stochastic or say fluctuating interfaces. And that's in particular what is called today the universality class of the Cardar-Parisi-Zhang equation. So I will be more precise in the future lecture, in the next lectures, I guess. But as you probably know, random matrix theory has played a very important role here in this context, and related to that is also the problem, which I will not have time to talk about. But as you probably know, this is related to directed polymers plus disorder, so in a disordered environment. So that means that these techniques of RMT actually have played a crucial role, a very important role during the last years. And I hope that I can give you the flavor of these applications of random matrix theory in physics. So in fact, although it's true that usually, in physicists, we like to think that RMT was sort of invented by a physicist. In fact, this is not totally true, and it turns out that RMT actually showed up before Wigner's work in the context of statistics. And in fact, it was introduced by a guy called John Wishart. Maybe you might have heard his name because he left his name to one important ensemble of RMT. And he was actually more interested in, so this was actually much before, because it was actually in at the end of the 20s. I think it was 2028. And basically what he was interested in was interested in correlations in time series. So basically, what you can have in mind is that you just suppose that you have, say, a vector. Let me denote it as x of t, and it has, say, n components. So you look at what happens at a given time t. So you will have x2. So you have a set of data. So typically, this xi of t, they might be the price of stock I at time t. So you might think of x of t as a kind of portfolio. You can also think of xi of t being say the temperature at the CTI on the day t, for instance. Okay, so that can be the stock price. That can be daily temperature. And what you are interested in, at least what statisticians are usually interested in, is in the correlation matrix. Say this CJK, which is defined by so these are the empirical correlations. So you just look at this. GT, it's KT, and then you just average over T. So so you have a correlation. You have naturally a matrix, okay, which characterizes the correlations between the different entries that you have here. Yeah, sorry, this should be an X. I'm sorry. It should be small x. And this object, as you see, is naturally is a random correlation matrix again. And you would like to know, how does this matrix look like? So it's random in the sense that it's xi's. You will take them if you want to make a model as random variables. And typically, the study of these kind of objects of random matrices play a crucial role in what is called principal component analysis. And this actually has a huge amount of applications, which I will not at all discuss, but it has actually many applications in the data analysis. Okay, in particular in financial data analysis, but not only. So that's just to show you that random matrices indeed, has a very wide spectrum of applications, ranging from nuclear physics to number theory, graph theory, disordered problem, and disordered systems. And okay, so I hope that I will have time to give you a little bit of more insight of the methods that we have to study this problem. Okay. Good. So let's go to the second point of this lecture, which has to do with the ensembles of RMT. So I will not be exhaustive because there were actually a very large list of RMT models and RMT ensembles, but I would like to discuss with you two main ensembles, which are first the Wigner matrices, and the second one the rotationally invariant ensembles, which to some extent are actually the most natural ones. Okay, so I will restrict myself somehow by following Wigner, and I will essentially discuss here the case of matrices which have a real spectrum. So again, for Wigner, this was quite natural because he was considering eigenvalues of Hermitian operators, which are of course real, and that means that I will stick to this idea. And to be more concrete, in fact, I will even look at the case where either the matrix is, say, real symmetric, or complex and Hermitian. Okay, because in these cases, of course, we know that the eigenvalues will be real, even though they are random. With probability 1, all the eigenvalues will be real. Sorry. So what I said, I think, having this in mind. So if you focus on this, if you stick to these ensembles, it's fair to say that you have basically two main categories of random matrices, I should say. So the first ensemble that I would like to discuss, and which are maybe the most natural one that you can think of, which are simply ensembles with independent entries. Independent, but respecting, of course, the symmetry, right? That they are real, or sorry, that they are symmetric or Hermitian, and that's basically what is called this is what we usually call Wigner matrices, because that's actually the matrices that Wigner introduces himself. So what do we have in mind here? Well, what I have in mind is in this case, the thing is relatively simple, is that so you have your matrix elements, MGK. So again, they might be complex or real. And I will just denote by X and Y, the real. Okay, so Xi and JK are both real, of course.
And this whole thing together.
Okay, so I heard something. So by definition, of course, X and Y's are just random and real. Okay, And now I want to write the joint PDF of this X eyes and Y eyes. Okay, so I want to look at the joint probability density function of a given realization of P of M. Okay, so that means that I want to really look at, it's like defining, if you want, a probability measure, a probability distribution on the ensembles of matrices. Okay, so I really want to write something like that. So of course I need to remember something, which is that my matrix M, it has to be a real, it has to be real symmetric or complex Hermitian. So that means that essentially you will fix, so you will take randomly all the elements that are in this upper triangle, including the diagonal, and then the rest. So the upper triangle here is just fixed by symmetry. Okay, so in other words, I mean, if I want really to be more explicit, this P of M here will be of that form. So these are IID. Okay, so I will fix. So that means that they are, well, they are independent. Sorry, they are not necessarily identical, but they are independent. And basically, so let me just define first so this is for the diagonal elements. Okay, so the one, sorry, that are on the diagonal. And then I need to fix the guys which are in this upper triangle here. So I will just have a product for j less than k. And then I will need to draw both the real part and the imaginary part. So this is for real. And then you might have a similar one for the imaginary part. Okay, so that's very, I mean, that's quite straightforward, and that defines a Wigner matrices. Now, maybe at this stage, it's already, I mean, if you have this picture in mind, I mean, it's quite useful to think about the number of degrees of freedom that you have in these matrices, because of course you see the matrix has n square elements, but the number of independent degrees of freedom is not n square, and because it's just these upper triangles elements, right, that are indeed indeed independent. And if you just count how many you have, so here you would have one guy, here you would have two guys, here you will have three guys, if you have four guys, etc. So you have just the sum. If you want to count the number of degrees of freedom, and these, well, it's quite easy to show. I mean, to compute, right? Is if you just look at the picture that I have, you will have 1 plus 2 plus 3 plus n, and that's just n minus 1 by 2. I will come to that later, but it's quite useful to have this in mind. Okay. So these are the Wigner matrices. Now, and in fact, I will not say too much about. I mean, in general, there is a whole literature on these Wigner matrices, but at the end, I will focus on a very special subclass. But the other useful ensemble is what I would like to call a rotationally invariant ensemble. And the idea is relatively easy to understand. If you suppose that, so let's stick now to be more concrete. I will just stick to real symmetric matrices, okay? Instead of, I mean, I will just discard for the moment the Hermitian, complex Hermitian. So I suppose that M is a real symmetric random matrices. And well, then you know that there exists that this matrix can be diagonalized, okay? And it can be just diagonalized by an orthogonal transformation. So that means that there exists a couple of, say, two matrices, O and lambda, where lambda is diagonal. Okay, so the lambda i's are just the eigenvalues of M. And O is just an orthogonal matrix. That means that O transpose equals to identity. And such that what? Well, such that you can indeed write M as, okay, so that O lambda O minus 1, or O transpose. Okay, so that's the thing. Now, the idea is that when you start to think about matrices and how to define an appropriate measure on the set of matrices that you are considering, it's quite relevant in many situations, and actually that was the case considered, for instance, in nuclear physics. It's quite natural to consider ensembles which are invariant under this kind of transformation. So in other words, the idea is that of a rotationally invariant ensemble, is to say that if you look at P of M, so if I look at a sum matrix, then it should be the same as, so instead, if I just do some similarity transformation on M, so that means that if I just do this kind of transformation, then basically the statistical weight should be the same. So essentially it means that the measure will only depend on the eigenvalues of your matrices. Okay. And this is called, these are called these rotationally invariant ensembles. And what happens, as I said, is that in such ensembles, the eigenvectors actually do not play an important role. We'll be a little bit more precise in a minute. But you see why. I mean, you see why, because as I told you, the probability measure of a matrix, because of this property, okay, I'm not showing it here, but you can feel it, should only depend on the set of eigenvalues. And so that means that the eigenvectors are a little bit spectators, and the eigenvectors do not play a very important role. They are not uninteresting at all, but okay, so I've seen one question. Yeah, what I mean by symmetry is relatively simple. So you see, if I look at my matrix M is either, suppose it's real. Okay, let's look at the real case. So that means real symmetric. So that means that Mij has to be equal to Mji. Okay. For I different from J. So in other words, that means that once you have drawn these random numbers here, then the symmetric ones which are on the lower triangle are just fixed. Okay, so they are not independent, and they should be exactly the same and fixed by this relation. On the other hand, the purely diagonal ones, so MII, are just, they are free to see whatever. I mean, to be whatever. Okay. Krishna, is it fine? Okay. Very good. So it turns out that which probability distribution is referred to fill the matrix element? Well, okay, well, this is fixed by that. So this is the answer number 1. At the moment, they are whatever they want. I will be a bit more specific in a while. So for any matrix in the rotationally invariant ensemble is same for any similarity transformation. Yes, so that's what is written here. So now, if I just, there is basically a theorem from that says that if you are looking at such rotationally invariant measure, then, and this is a theorem which is due to Weil, what you can show, I mean, it's quite intuitive to understand why it's like that, but the P of M should be of that form. It should be of the form exponential of minus trace of some function of M. So it's clear that at least one can easily understand that if P of M has this property, since the trace of M or the trace of any polynomials of M, trace of M squared, trace of M cubed, is independent, I mean, does not depend, or is invariant, if you want, under such a transformation, then it's pretty clear that if exponential of, I mean, if the measure is of that type, then it is rotationally invariant. Okay, it's a bit, of course, more difficult to show the other way around, but it turns out that this is true. And in fact, this is just equivalent. So I have shown these two kinds of ensembles, okay? Ones are the Wigner ensembles. So Wigner, you really take, or Wigner matrices, you take your matrix and you fill it with random numbers with the constraints that you have to respect this symmetry, okay? And you have these other ensembles which are rotationally invariant and which are, I mean, constructed with this prescription and which at the end are of that form. Okay, so I should say that here V of M is some function that you can choose priori as you wish, and it will depend on the model that you have to look at. Now, a natural question then comes is whether, I mean, are these two ensembles completely disjoint, or is there some intersection? And what is, if it exists, what is the intersection? So there is a very nice and simple theorems which says that the only matrices that belong to the ensembles A, Wigner, or B, rotationally invariant, are the Gaussian random matrices. Okay, so in a sense, we see that the Gaussian measure, as we know from standard probability theory, it also plays a role in this context of random matrices. And in fact, so that's something that I will just and which is from the 60s. Basically, that says the following is that the only ensembles that belong, or the only matrices, if you want, that belong to A, that means Wigner, and B, are of a simple form, are the Gaussian ensembles. Okay, so that means that really P of M, so the only matrices that are of the form that I mentioned, so they are Gaussian, so that means that you can just write it as exponential of trace M squared minus B trace M. and there is some normalization factor. So, well, you see, it's clear that they belong to the case B, right? Because it's clear that they are of that form. Trace is a linear operation, so V of m is just am squared plus bm. Now, it's not completely evident that this kind of measure here defines a Wigner matrix. And that's, I think, instructive, just since we haven't done yet any concrete computation. Maybe it's good to do one, just to start with something. And I just want to show you that this is indeed a Wigner matrices. Okay. That this is of type A. That means Wigner. Okay, so let me just make a short stop before doing that. I see that the lower triangular. Okay, sorry. So so for any matrix notation. Yes. So Fabien Mathieu, can you please say again what we study in the context of rotationally invariant ones? Because the spectrum is then just a collection of random numbers given from scratch. No. Well, no, I mean, they are not given from scratch because for rotationally invariant ensemble, you see that you have a strong constraint at the end, is that the measure on so here I've really defined a probability not on the matrix elements, but on the matrix as a whole. And at the moment, I mean, usually it's very hard to come back, I mean, to translate this into a probability measure for the elements. There is one case where you can do that, and this is the one that I want to show you now. This is the Gaussian case. But otherwise, you see, you really define, instead of defining a measure on the matrix elements, which is what Wigner is doing, here you really define a probability measure on the set of matrices. Okay. I hope I answered your question. Okay. But it turns out that this is one case where precisely we can do both, and let's see what it gives. So let's just try to rewrite this exponential weight here. So let's do it. Okay, so this is just exponential of what? So let's just rewrite what this trace m square is. So by definition, this is just a sum of gk, m, gk, m, mgk, mkj. Okay, that's the definition of a trace of m squared. And then here I just have the sum, say over j, mjj. Okay, so here let me just rewrite this the first terms here by separating in the first in this double sum here. I will separate the diagonal terms j equals to k and j different not equal to k. Okay, so that's what it gives. It's just the sum over j mjj squared, and then I get minus a sum from j different from k of mgk times mkj, but mkj, because the matrix is symmetric, has to satisfy this property. Okay, so that means simply that here I will get a squared. And then I have a simple term here, which is minus b sum over j mjj. Okay, so now if you just gather all the terms, what you easily see, no, is that this has almost the Wigner form. Okay, but if you go to the way, if you go back to the way I define the Wigner measure and the way this is usually defined, is that here you see the product is for j strictly less than k. And here, of course, I can use on top of that the property that the exponential of the sum is the product of the exponentials. And therefore, you would simply get the following. So let's maybe first with the okay, so I will just get exponential of minus a j mg squared. So these are just the measure, if you want, on the diagonal terms. And now this sum here, I just rewrite it in a slightly different way, which is minus 2a sum for j strictly less than k of mgk squared. Okay, and indeed now at the end of the day, you can still write it exactly as a Wigner matrix should look like, because that will be exponential of a minus mj, and then I will have indeed the product of I less than j exponential of minus 2i minus ij squared. And this is exactly of the Wigner form. Okay, so that's really so that tells you that this matrix is indeed so that means that belongs to A. Now, certainly, and at this stage, I just make this remark, which I think is important, is that basically for b equals 0, okay, so that's the most natural, I mean, well-studied model that we will come back to in a minute. What you see is that the diagonal terms and the off-diagonal terms, these are Gaussian random variables, but they are not exactly identical. In fact, the variance of the diagonal terms, oops, sorry, is just twice the variance of the off-diagonal terms. Okay, so let me just. So that means that they fluctuate a little bit more. But this is quite important if you really want to have a real symmetric matrix. Okay. So we have seen these two ensembles, these two sets of ensembles. We have seen that they have a nice intersection, and in fact, as you can guess, this intersection is probably defines probably the most interesting ensembles, and that's the one that we will study in the following. So basically, in the following, that means today, but also in the forthcoming days, I will set b equals 0, and we will focus and focus on the Gaussian ensemble. Okay, so just some definition. So here I mostly discuss the case for where M was real and symmetric. And this ensemble is well known. Maybe you have already heard about it. It is called the Gaussian orthogonal ensemble. So Gaussian is quite clear. Ensemble is also clear. Orthogonal, you see, it does not mean that the matrices themselves are orthogonal, but the measure is invariant under orthogonal transformations. Okay, so orthogonal is really in that sense. Now, I discussed here, as I said, the real symmetric case. Now, if I was, I mean, the other ensembles which is interesting and which we will discuss in the following is the case where instead of having real, you can have complex elements, but then M needs to be Hermitian. And in this case, this is what we call the Gaussian unitary ensemble. So again, unitary in the same sense. It's not that we are considering unitary matrices, but the measure is invariant under unitary transformation. Okay, so that means that when you have a complex, Hermitian matrix, then what I wrote here, I mean, needs to be slightly modified instead of having here. So you can still write, you can still diagonalize M under this form, but O, I mean, your matrix O here, which usually we denote by U, is now unitary and not orthogonal. Okay, so that's in that sense that we are talking about Gaussian unitary ensemble. Okay, and so usually, and that's the acronym that we will use later on because so this is the GOE, and this is the GUE. Okay, so this is all very nice. We have these ensembles and they are well defined, but you see they are still a little bit formal. And the reason is that if you go back to what we wrote there, it's nice to have something like that. So you know indeed that your matrix can be diagonalized. And I told you that for such invariant ensembles, such that the Gaussian orthogonal or Gaussian unitary ensembles, the probability measure actually depends only on the eigenvalues. But it's clear that what you would really like to have is the joint distribution of these eigenvalues. Okay, so in other words, if you think about these Gaussian matrices, you have here a relatively nice way and concrete way, in fact, to define these matrices, so you can easily simulate them on your computer, because you take all these numbers as random and then you fill the matrix as they, at the correct place where they should be, MJK. But then, of course, what you would like to know, in many cases, what you would like to know is to say something about the eigenvalues and the eigenvectors. So what you really want to do now, and that's what we are going to do, it will not be exhaustive, but I will give you the main ideas. What you really want to look at is to look at the joint law of eigenvalues and eventually eigenvectors. But I already told you that the eigenvectors in these ensembles are a little bit boring. But I would like to know something about the eigenvalues for, say, the GOE. Okay? So that's what we will do in the following. So I will start again. I will focus here on the GOE. That means that I will look at M, which is equal to M transpose and real. Okay. And of course, I want. So the idea is to go to the diagonal form. Okay. So I know that I can write M under this form, O lambda, O transpose, or O minus 1, with again lambda and O transpose. It's just the identity. So let me come back to this number of degrees of freedom that we had before, just to understand a little bit what we want to do. The main idea, if you want, is just to perform a change of variables. The idea is that I gave you a P of M, so you have a measure on the M, which is basically defined by the MG case. Okay, and you would like to go. So instead of formulating in terms of a measure on the MJ case, you would like to have a measure on lambda and O, basically. Okay, so maybe one thing that it's quite useful to write here is that, well, it's clear that lambda, this lambda here, encodes the eigenvalues, and the O there encodes the eigenvectors. I guess you remember your course on standard linear algebra that you just construct the matrix O by just putting inside the coordinates of your eigenvectors. Okay. So the idea is, I mean, conceptually is relatively simple. I think is that you would like to, instead of having a measure in the probability measure of MJ case, you really want to go to this lambda and O things. Okay, so it's just if just to count how it. I just want to it's just a remark, but we have counted already the number of degrees of freedom. We have already seen that they were equal to n plus 1 by 2. So basically this sum here, I want to see as the sum of the number of eigenvalues. So this is n, and then the number of degrees of freedom associated to O. And since this is, so here, of course, it's just some algebra, but you can just realize that this is just n minus 1 by 2. Okay, so this is just a very simple relation, but you can indeed check that if you have an orthogonal matrix of size n, so naively, okay, it's a random matrix, so it's a matrix, it has n square entries, but because of this relation, of course, you have much less degrees of freedom, and this is precisely the number of freedom that you have. So what you really want to do is, through this change of variable, is pass, I mean, or go through, if you want, the P of M, which is quite simple, right? I mean, which is, in this case, which was just something like that. You would like to go to a probability measure on the lambdas, so that's your eigenvalues and your matrix O. Okay. So in principle, I mean, you see, I mean, we are doing something which is in principle quite familiar, and we know that these two distribution here, they are related through a Jacobian, and this involves a complicated determinant to compute. So more precisely, what I want to say is that P of lambda 1, lambda n, and O, well, this will be generically given by P of M times the Jacobian. So that means the determinant of some matrix J, and this matrix J is just the matrix of the partial derivatives. Okay, so I will not write explicitly this J matrix. Okay, but J, quote unquote, if you want, because I don't want to write it explicitly, but it is of that form, right? So it just the matrix of partial derivative of dmij d lambda k and the mij divided by DOKL. So it's quite complicated matrix. I mean, it's an n square. I mean, it's a matrix of size. The size of this matrix is quite big. And that's why it's a bit complicated to compute its determinant. But This is just the number of independent degrees of freedom that you have, right? So this is n plus 1 by 2 cross n plus 1 by 2. So since it's not really a full course on random matrices, I don't want to bother you with the computation of this determinant given this matrix, but simply give you the result because it will be extremely useful in the following. In fact, quite remarkably, it turns out that the determinant of J, so this is for GOE, the determinant of J written this way has actually a very simple structure. And this is just what I'm writing here. So this is this beautiful result. Now, so it's remarkably simple, and that's why at the end you see the distribution. So what is quite remarkable, it is indeed simple, but it is also independent of O. Okay, so the matrix elements OKL actually do not enter into this. Okay, so if you look at again at this distribution here, that tells you that the distribution of the lambda i's and O actually are just completely decoupled, because P of M, maybe I should write it, P of M actually depends only on lambda i's, right? Because in this case that we are studying here, P of M is just exponential of A trace M squared, and that's just exponential of A sum over the lambda I squared. So that means that, let me just write it explicitly, I think it will be better. That means that the joint distribution, now we got it, of the lambda i's and the O's, so that means the eigenvectors essentially, is just 1 over Zn, some constant. And then I get this product here. Okay, so so you have this nice expression. Just want to displace it a little bit. So let me just write it in this way. I've introduced, maybe I should denote it here. There is here a power beta. So for GOE, beta is equal to 1. Okay, so that's exactly what I showed you here, right? So that comes, the 1 is just this guy. Now, I haven't done the computation for GUE, but it's very similar. And it turns out that for GUE, the expression is exactly given by the same. So that means by this guy. Only beta is different. And beta is equal to 2. So that's quite remarkable, of course. Now, I just want to say something about this quantity here. Yes, okay. I want to answer this question because it's sufficiently interesting, I think. What would happen? The question is, what would happen if there is degeneracy, because then determinant of J is equal to 0? Yeah, that's a good question. The point is that we are here dealing with random matrices, and the probability, and that means that I take these entries as random variables and I draw them from a continuous distribution. Okay, so typically a Gaussian here, as we have seen. And that means that if you take two random, think about, so the probability, if you want, that two eigenvalues exactly coincide is basically equal to 0. Okay, and we will see actually that this is indeed the case in a minute, but you can already feel it, no, that if you take two random variables which are Gaussian, if you look at their the probability that they are exactly the same, I mean, this probability is 0. So if you want, this define a set of events which has measure 0. Okay, is that okay? I suppose so. Okay, I just maybe want to make one remark. Maybe this guy here has a very nice expression, and this is called a Vandermonde determinant. Okay, and this is just to remind you some basic facts from linear algebra. But I just want to discuss what the Vandermonde determinant is. So let me define this matrix Vn, which is an n by n matrix, and it is defined from the set of random of numbers x1, x2, xn, and they are different from each other's. And I look at this matrix, which has this very nice structure, which is like that. So I first consider the variable x1, and I consider 1, x1, x1 squared, x1 cube, up to x1 to the power n minus 1. And then I do the same with x2. And I repeat that up to xn. So it's an n by n matrix, obviously. And if you look at if you compute the determinant of this, well, okay, I mean, you can just do easily the case n equals 2, for instance, just to get fun. This is just 1, x1, x2. So this is v2. Now, if you compute the determinant of v2, well, it's very simple in this case. This is just x2 minus x1. Now, it turns out that if you look at Vn here, it's a standard exercise in linear algebra. I'm sure that many of you have done that. This is just the product of I less than j, xj minus xi. So that means that what we have here, this term here is just the absolute value of a Vandermonde determinant. Okay, so it's quite nice. I mean, because it starts to have. We would like to understand this measure here, and that's what we are going to do following Dyson. In a minute, we would like to understand a little bit better what is the meaning of this. Is there any nice physical interpretation behind this? There is already one thing to notice, and this is related to the question that I answered to Maynak. You see that because of this Vandermonde term, which here comes from the Jacobian, you see that the probability that two lambda i's are exactly equal. I mean, this probability exactly equals to 0. So that means that really these eigenvalues, they somehow repel each other. Okay, so they really don't want to stay close to each other, and there is some kind of level repulsion. Okay, and that's what really this is saying. And this is something that you can already easily compute. You can look at n equals 2, for instance, and do this thing. I mean, it does nothing to do with the large n properties. It's really something that related to the fact that I was mentioning a little bit before to this question, that the probability that two eigenvalues exactly coincide actually goes to 0. And so there is some repulsion, and in some sense, physically, this is somewhat reminiscent of fermions. Okay, I mean, roughly speaking, fermions are particles which don't want to occupy the same eigenstates. And in some way, it's good to think about. It's good to think of these eigenvalues as the position of fermions. And later on in the course, I mean, this will be even more precise. But before discussing fermions, I want to discuss the connection to, to the Dyson's log gas, the Coulomb gas approach. And here I just want to make, I have to, you see, I have not yet settled this constant A here. So there are various choices. If you look at in the literature, people usually, have different ways to choose them. Of course, it's just a matter of scale. So you can just, pass from one value of A to another value of A by a rescaling of A. Okay, but at some point you need to make a choice. And for this course, I will, at least on RMT, I choose the following. So basically, I choose A to be beta n over 2. So that means that I will just now. So since this O actually doesn't enter on the right-hand side here, I can now integrate. So if I want to look to compute the marginals of over the lambda i's, then I just need to integrate over this the orthogonal group. So that gives me a number which corresponds to the total integral, but it does not couple the matrix elements of O and lambda i's. So this is already, if you want, up to a prefactor. This is just the joint distribution of the eigenvalues only, and that's the quantity that I will look at. That I will focus on in the following. So I will just look at P of lambda 1, lambda n. So that means that I have just so there is some normalization. Let me call it Bn at the moment, and I will define it this way. I will define it as exponential of minus beta n by 2, the sum, and the beta is a bit arbitrary, but you will see why in a minute what I decided to put that. And then I have this lambda j power beta. So as we will see, I chose, so the important thing to notice here is this factor n. Okay, this one is not innocent. And I chose it in purpose. The purpose is that, as you will see, when we want to take the large n limit, we will see that with this scaling here, it turns out the typical value of the lambda i's are of order 1. Okay, I will be a bit more concrete in a minute, maybe only tomorrow, but at least that's the idea of this choice. So that means that essentially, if I go back to the, okay, I haven't said it here, but if you go back to this, basically to this, so if I want to write this distribution in this way, so if I want to come back, if you want, to the matrix elements, that means that the variance of the diagonal terms are of order 1 over n. In fact, they are exactly 1 over n with this choice for beta equals 1. And they are basically 1 over 2n of this guy. But what is important to have in mind is that the variance is of order 1 over n. This might appear a little bit artificial at this stage, but again, this is just a matter of rescaling, and you will see why in a minute, I hope.
Gregory, one small question. So, if you look at the joint distribution of the lambdas and O's, I guess if you integrated out the lambdas, one would kind of get a like constant, which gives the distribution of the eigenvectors, right?
Yes, exactly. So that's a good point. So indeed, so that's a constant in the sense that it does not depend on O's, and that means that the matrix O itself, which encodes the eigenvectors, is uniformly distributed over the orthogonal group. So that means that they are all equiprobable, if you want.
Okay, so this is kind of it's not obvious like it should have been. Like, is there some simple way to understand this, or it just happens?
It has really, it's done somehow by construct. it's hidden more or less there. It's hidden in the fact that somehow the probability measure, you see that if you impose that, somehow it means that the P of M can only depend on the eigenvalues of M.
Okay.
And if it only depends on the eigenvalues of M, that means that all the eigenvectors are equally distributed.
Okay.
Or uniformly distributed.
Right. Okay. Thanks.
Okay. So in a sense, in these ensembles, the eigenvectors, I mean, play a very minor role.
Okay.
At least if you do not specify it. I mean, okay, of course you can condition, say, for instance, how does the eigenvalues, how does the eigenvectors corresponding to the eigenvalues looks like, or these kind of questions. But even this kind of question, in fact, I mean, are a little bit less interesting than for other ensembles.
Okay.
If I could add to it, like, I think this is a consequence of the rotational invariance of the ensemble, because
Yeah.
when you can rotate it arbitrarily, then eigenvectors change, but eigenvalues
sure.
don't change.
Yeah, exactly. So that's
so-
what I was saying. I mean, that it's hidden in I mean, in the way the things are constructed. But I agree. I mean, that this is not completely obvious. And in fact, the computation is not obvious at all. I mean, when you really do the computation of this determinant of the Jacobian, right? Well, it's not clear that, but okay, this is true. Okay. So if I have I have what, 10 minutes more or less, or?
Yeah.
Okay. So now I want to understand this in a more physical way. So up to now, one could say this is pure math, right? I mean, there is no physics there. And what I want to discuss now is the Coulomb gas approach. This is due to Dyson. And okay, maybe just to come back. So you are here, right? We just end up this, and we are moving to this number 3 here. Okay, so that's a capital 3, by the way. Okay, so the idea might look a little bit, I mean, quite simple at the beginning, is just to rewrite this term. So to rewrite this term in a more physical way. Physical means that I want to have in mind that, okay, statistical physics. I want to have in mind statistical physics. And what I would like to see is that it turns out that one can write, that will be just some rewriting at the moment. We know that if we want to interpret this as a Boltzmann weight, so that should be exponential of minus beta something. Well, this has to be re-exponentiated. So that means that I will start by rewriting this guy as exponential of, say, beta less than j. So there's nothing really here, right? I mean, I just rewrote the simple things, and maybe it's convenient to make it symmetric. So I prefer to write it in this way. But now you see that what is nice is that if you combine this, so if you combine this identity, inject it here, then you start to observe a nice structure, right? Because that tells you that basically your probability weight, on the lambdas. Okay, so you had your Bn, so keep your Bn. But then I claim that I can still write it in this way. And E is just the sum of two contributions. One that comes for this one. So I took out the beta outside. So this is just, and the minus sign also. So this is n by 2 times the sum lambda I squared. Okay. And now this term here, the interacting term, the interaction term, is just minus half. Okay. So that's your interaction energy. But what is quite nice now is that if you look at these equations, then you really want to see the lambda i's as the positions of some particles, of say charged particles, which are confined in an harmonic potential, and which are sort of interacting via this log term. Okay, so I saw the question. I will answer to them at the end, if you don't mind. I just want to finish the explanation here. So again, this provides a very nice interpretations in the sense that the lambda i's, I just want to see the lambda i's as the positions. Just write it explicitly. Charged particles interacting via the log potential. So this is actually the Coulomb interaction, but in 2D. So I should better say the 2D Coulomb interaction. And confined on a line. Within a quadratic well, or put a harmonic well if you want. Okay, so it's really that at the end, I really want to understand this model as, so I have this, if I look at the lambda i's, so I would have, oops. Okay, so I have a quadratic potential, and I have my particles, which are living on the line. And the important point again is that they actually are interacting via the Coulomb interaction here in 2D. Okay, so again, this is not the 1D Coulomb gas, which would be linear mod xi of minus xi, and that's what we usually. So this is a Coulomb gas where the particles live on the line and interact via the 2D Coulomb interaction, and that's what is called the log gas. Okay, and this was introduced again by Dyson. And what is quite nice again is that we moved now from a purely mathematical problem where you had eigenvalues, and we translated it into a statistical mechanics problem, which is these particles in a quadratic potential. Okay. which is basically lambda squared. So you immediately see, and something that I should add is that the interaction, of course, is repulsive. And this is important because we have already seen that these eigenvalues are actually experiencing some level repulsion. And that means that we have here an interaction which is repulsive. So basically, a good way of thinking about this problem now, if I look at these particles, is that there is a competition between the potential well, which would like to push all the particles down to the center. And so that's what, if there was no interaction, the ground state would be basically constituted of all the particles at the center, collapsed. But because of this repulsive interaction, of course, they cannot do that, okay? And that's what makes this problem interesting, is that there is a nice competition between confinement and the repulsive interactions. Okay, and this gives rise actually to a very nice, interesting physics, collective effects that we will describe in more detail next time, I guess. So I just, yeah, so that's basically where I will stop today. I think it's a good place to stop. Maybe before I can just try to take the questions that I see in the chat. So Raoul, why choose the coefficient in the exponential as opposed to alpha n by 2, where alpha is arbitrary? Okay, so maybe now you understood is that this beta, which was a bit, if you remember, I introduced it in a quite artificial way here. But I want to see this beta eventually as a temperature. So this means that I want to have basically this A here, I would like to have a beta there, such that I really can write this as a Boltzmann weight. Otherwise, I would have a beta in terms also in the energy, which is, I mean, which could be possible, of course, but which is not the most natural way. So I hope this answers your question, Raoul. Alors, Ramgopal, GOE are rotationally invariant and their member matrices are real symmetric. Can you elaborate it more clearly? GOE are rotationally invariant. Yes. So that's what I tried to show with these computations, okay? So basically, I showed you that there are two kinds of ensembles. First ensembles are the Wigner ensembles, okay? In Wigner, you really think in terms of the elements of your matrices. It's more like you are in front of your computer and you want to simulate a random matrix. And somehow the most natural way to do is probably, as Wigner did, is to choose the elements of your matrices as independent random variables. Not necessarily identical, but at least there can be so basically, the members are real symmetric, and you just have random elements. On the other hand, I define these other sets of rotationally invariant ensembles, which are really constructed more from the point of view of symmetry. And there you really want to have, you define your probability measure, not on the entries of your matrix, but on the matrix themselves, okay, which is really different if you think a little bit, which is really different. And that gives rise to this kind of probability measures, which are rotationally invariant in the sense that you have this symmetry, okay? So P of M and P of O, M, O minus 1, because of the trace here, obviously have the same probability weight. Now, you can ask, is it possible? I mean, what is the intersection, if any, between these two sets, of random matrices? And the answer is that the only intersection consists of these Gaussian matrices, which are the one that I show right now, which are of that form. So it's clear that they are rotationally invariant, okay? Because the trace of m squared, if I start to do some similarity transformation, that will not change, okay? Because the trace is invariant under such transformation. Now, what is less clear is that these matrices, which defines a rotationally invariant ensemble, are also real symmetric, and they are of the type of the Wigner one. And that's what I showed in this computation, is that if you really write what the weight is, at the end of the day, what you see is that this is equivalent to defining the probability measures of M in terms of the matrix elements, and the distributions of the matrix elements are just written here. Okay, notice there is a small misprint here. Did I answer your question, Ram Gopal? Okay, great. So since there is no kinetic term, how do we define the dynamics, equations of motion of these charged particles? Yeah, okay. If you want, you can just so that means that you have a Hamiltonian, if you want, which is just the kinetic energy plus the interaction part, and potential energy, if you want. Potential energy includes the interaction between the particles and the confining energy. But since there is no coupling, if you want, between the impulse, the momenta, pi squared, and this xi's, I mean, eventually this is just factorization in the partition function. So I can just discard this term. Okay, they are just spectators, if you want. They do not. If you want to define a dynamics, of course, you need to include this kinetic term. But here I'm just looking at the equilibrium and thermodynamical behavior. Okay, Harry, if a further restriction of positive semi-definiteness is imposed, is anything universal known about the characteristics of eigenvalue distribution? The answer, okay. I don't know very well these ensembles, but I do believe that they actually define another set. I mean, yeah, I'm pretty sure, in fact, yeah, okay. Yeah, this indeed defines a constrained ensembles, which you can still study by various means, but you will end up on different kinds of ensembles. I don't know about the universality properties of these ensembles. I would naively guess that they are as universal as the Gaussian ensembles are, which I will discuss a bit later. That means that my guess is that if there is a kind of central limit theorem in this random matrix ensembles, which is that if the matrices, if for the Wigner case, okay, if I look at the Wigner matrices, if they have a second moment which is well defined, then in the large n limit, basically the Wigner matrices will converge to something which looks very much like a Gaussian orthogonal or Gaussian unitary ensemble in the large n limit, and it will be exactly similar in the limit when n goes to infinity. I guess that this is the same if you start to impose some restriction as you have in mind, Harry. But I must say that I don't have any concrete reference for that. But I can, yeah, probably it's, I guess that people have studied that though.
Yeah, in certain applications, like you sort of encounter this restriction. So I was thinking, like, if there is a universal known about it.
I see. Yeah, I guess it should there should be some universal behavior. Pretty sure.
I think Wishart ensembles have this property of positive semi-definiteness.
But
well, Wishart is yet a bit different, but
yeah, like it's defined like x times x dagger, so
yeah,
it's positive semi-definite. So
yeah, well, if you well, it depends. Yeah, okay, yeah, that's one way of seeing it. Yeah.
Okay, thanks.
But these are not, I think, the only ones that are positive semi-definite. Wishart is of that type, but this is not this is not the full story about positive semi-definite, I think. I mean, not that I think, I'm sure.
Some other positive definite matrix, right?
Sorry?
I think Wishart ensembles are like you sort of define some auxiliary random variables and like from them
Yes.
you construct quadratic forms and they sort of behave.
Sure, sure. No, what I'm saying is that Wishart matrices are, of course, positive semi-definite, but not all positive definite matrices are of Wishart type. That was my point.
Okay. Thank you.
Okay.
Is there any other question? Yeah, I think there's one more question.
Yeah, okay, it's true. I mean, okay, I haven't. If you can order them, actually, it's the ordering is not okay. There is this question. Maybe it's interesting already to answer it. Raoul says, I guess the form of p lambda are not ordered. So that's what the lambda i's are not ordered. What is the form if they are ordered? Well, it is basically that you have just 1 over factorial n, I mean, in between. But because so that's important to notice that the joint distribution, which you can read it here or even say here, it's completely invariant under permutations of the lambda i's. Okay. So all the sectors that you can order in a prescribed way, so this is called these Weil chambers, if you want, they are just all equivalent. So if I start to write or impose that the lambda i's are ordered, then I will have to multiply this by some n factorial here. So, but it will not change the shape of the of the joint distribution. So the question is it similar to have a similar level repulsion in non-random matrices? Well, in fact, it's not really. It's not a property of. That's a good point. I mean, this is a property of linear algebra. I mean, this level repulsion. I mean, in quantum mechanics, in fact, this is also known. I mean, but indeed, I mean, this is generically. If you look at a random matrix, I mean, if you look at a matrix, sorry. Typically, it will really feel level repulsion. Okay, so it's very unlikely that you will have coinciding eigenvalues. Yeah, it's a bit it's a bit difficult to make a more precise answer to the question. If so, what properties must the matrix have? Yeah, okay, again, if the question is more the other way around, I mean, if you want to have a matrix which like to have a coinciding eigenvalues, then you really to design it in a special way.
Hi, sir. I wanted to know whether there are other kinds of interaction potential which are possible in random matrices. Here it's log. So is there any other example where it's not log gas, something else, which is coming from random matrices?
Sure, yeah. So in fact, in random matrices, you will always have a log. I mean, and you will never get this interacting potential that you like, Jitendra. In fact, the deep reason is always the same, is that the interactions that you get from the between the eigenvalues in all the matrix ensembles, in fact, even though, I mean, even the ones that are yeah, even if you go, for instance, to a higher dimension. So here I have been discussing real spectra, but if you look at more general matrices where you would have complex eigenvalues like G-Niebuhr ensembles or so on, the interactions always come from this kind of manipulation. So it really comes from this van der Monde because it has this deep root in linear algebra. Okay, so that's one thing. So you can have some variant of it. For instance, instead of having log of lambda I plus minus lambda j, you could have on top of that log of lambda I plus lambda j. But this is just a kind of mirror symmetry. For instance, this is what you can get in some okay, in some models, in some fermion models which are related to random matrices. So this might appear, but generically you will get some variance around that.
So is that something like level attraction, lambda I plus lambda j?
Yeah, exactly. Yeah.
Okay.
Yeah. So it's as far as I know, at least. Okay, I'm not saying that maybe you can come up with a very, I mean, exotic result, exotic matrix models, but all the matrix models that people, I mean, that I know, I should say, they are all of that form.
Thank you.
Okay, I have this thing. Suppose you want to physically construct this Coulomb gas in one dimension, the 2D Coulomb. So do I need infinite potential in the other direction to close it? Because I guess any other potential, if you put, it will give you a spread, right?
Yes, absolutely. So yeah. So I guess, so indeed, so that means that, so that's typically what happens when you look at this more general model that I just mentioned here. Which is, sorry, yes, well, this one, this V of M, okay? So if you look at this kind of model here, this one, sorry. So if you look at the joint distribution of the eigenvalues, then you will have typically the van der Monde. So it would look like something like that. If you really look at it, this case, if you look at the P of lambda i's, so you will have, as usual, the van der Monde term, beta equals 1 or 2, whatever. And then, generically, you will have this term. And indeed, depending, can you read it?
Yes, I can read it. Yes.
So depending on V, so essentially, if V is sufficiently confining, basically if it goes faster than logarithmic, then it will confine the particles on a finite support. And many things then become sort of universal, especially if you look at the edge, or at least if you look at the local correlations, they tend to be pretty universal. But if, so this is true as long as V grows faster than logarithmic. So any potential that you might think of could do the job, but there are ensembles, for instance, what is called the Cauchy ensembles, where you have logarithmic growth, which is a kind of borderline. Then you cease to have a finite support, and then you have the eigenvalues are then spread up over the real line. But in fact, for a large class of potentials, indeed, all the phenomenology that you get from the Gaussian case are there. And that's also why, I mean, maybe that's also why these Gaussian ensembles actually are very interesting, is that it's not only that we can compute things with them, but in fact, there is a quite important dose of universality. And many things that you will learn from the Gaussian ensembles remain true, at least in the large n limit. And there are some differences, and I think I will try to discuss this. I wanted to discuss this a little bit more in the next lecture.
I think there's no more questions. So maybe we'll just stop here today, and
okay,
we'll again see you tomorrow.